Welcome to lesson 5.2, graphing derivatives and antiderivatives. In this video, we're going to do another example of graphing our antiderivative. In this case, we've been given a graph of our first derivative, and we're going to use that to find the graph of our second derivative, and then also a possible graph of our first derivative. Now, unlike the previous example, we have not been given a starting point for the graph of our first function. I think I said that wrong earlier. Our regular f of x. So let's start with what we did last time with our set of instructions here. The first thing we're going to do is make a number line of our first derivative. Now we've got this nice straight line going from someplace down at negative infinity up to 0, 2. And when we're looking for our critical numbers. Now, in this case, we only have one spot that we can see that it crosses our x-axis, and that's at our -2. So we'll go ahead and mark our critical number here at -2. And then it's not really crossing, at least we can't see that it's crossing anywhere else. Now, the second piece of information that we're looking at here is what the slope is going to be on our original function. And so when our first derivative is negative, that means we've got a negative slope on our original function. And when our first derivative is positive, it means we've got a positive slope on our original function. So we'll go ahead and put that information in there. With this, we're going to try and graph our second derivative. Okay, we could actually get most of the information without graphing it, but we're just going to go ahead and do that for the moment. So anytime we have a linear function, when we take the derivative of that, we should have a horizontal line, right? Because it's not changing any. There's no variable as far as the change of the slope in this. And so in this case, our slope looks like it's 1. So I could actually graph this just as simply as going like this, right across here at 1. Now, if you take a look at this point right here at 0, 2, this point right here, there's a sharp turn. Okay, we're transitioning from a linear function to what appears to be, or what could be, a quadratic function. Okay, and so this is a sharp turn, which means that there is no derivative for this. Sharp turn. Let's see if I can spell that right. Okay, and so if there's no derivative at this point, then we have to leave this as an open circle on x equals 0. We're also going to need to leave it as an open circle when we take a look at this next portion right here. Now, if we looked at this and considered that this might just simply be, if we looked at this line, we could consider this area right here as the function y equals x squared plus 2. It's got a vertical shift going up. We're just, again, with our knowledge of functions, parent functions in particular, this would look like, or has the potential to be for sure, a quadratic function. Our first is 0, the second position will be at 1, and in this case, it's just been shifted up 2. So we could look at this like that. If this is, so if, then our derivative, oops, try and write this out right, then our y prime in this case. Now keep in mind, this is our first derivative and second derivative, but relative to each other, our y prime would then be 2x. Well, 2x is an easy one to graph. We start here at the center right here, and we just try and watch our line going up right like this, and it would go on forever in this case. Okay, again, open circle, because it's got that sharp turn there. It's just simply not defined. Okay, so now that we've got this, we're once again looking for the critical points on our second derivative. And that's going to come again where it's equal to 0 or it's not defined. Now, we would have a point that's equal to 0 at 0, but it's undefined. So either way, we're picking up that point. So I'm going to go ahead and, I should have changed colors earlier, but we're going to go ahead and pick up that point here at 0 because it's undefined. And we're now going to look at the value of this because this is going to show us concavity. In this case, everything on the negative side and everything on the positive side is positive. And that's going to make it so that we know we have something that has got a very large smile on it. Something similar to a quadratic or a even numbered polynomial function. So our next thing is to look at the combination between these two. I'm going to draw another number line. You don't have to. It's not necessary. But I'm going to do this similar to the other example we did. And I'm going to take our critical points here at -2 and 0. And we're going to take a look at what's actually happening. Okay, I'm going to just kind of draw my my lines going down here. So we've got basically 3 partitions here. With our second derivative, we know that everything is concave up. Okay, so, and with our first derivative, we know that it's going in a direction. So this is coming, if we looked at this, it's a negative slope, positive concavity. So we're looking at something like this. Okay, our second section here, we're going again, or we got a positive slope now, still positive concavity. So we're doing something like this. And this last portion, you know, we've got this undefined point in here. But what it's showing us is that we're still going in a positive direction and we still have a positive concavity, which means it's continuing to do this. Now, whether this change here is going to mean it's going to go up sharper or a little bit more relaxed will remain kind of unknown. But we do know that when we look at our functions, if we took an x cubed function, the derivative of that would be 3x squared. So we go from a trinomial to from a cubic function to a squared function, and then this goes to a linear function. And so, if we are looking at this as a quadratic, as a squared function, then it's likely that we're looking at something that's more of a cubed function on our original function. Okay, so when we go to graph it, one of the things to keep in mind is that we do not know where it's going to fall on this vertical line. The one thing that not having a starting point to really fix it in here is it gives us a lot of flexibility. Now, when we were looking at this straight line, remember we just talked about the functions go from cube to squared to linear. If we're going backwards, we're going from a linear to a squared. I would say everything on this negative side of our number line is going to be squared. And so if we were to just kind of plot some points, we just started down here at 2.22 or -2, -2. A quadratic or a squared function follows along these. It goes up 1 over 1 up 2, or sorry, over 1 up 1 over 2 up 4, right? Because you're squaring the values. So we could come pretty close to what this is supposed to be by just following, whoops, nice curve here. And my drawing skills are improving, but they're still far from where I'd like them to be. But then right here at our 202, this part where it crosses our y-axis, it changes from a squared function to conceivably a cubed function. Now, we don't have anything that tells us that that's actually what it is. It could be something else. This is an assumption that you're allowed to make given what you know about the information that you've been given. And so this right here would be going in a cubic motion. Again, we still have a positive concavity, still going in a positive direction, and so it could be doing something like this. We just don't really know. Okay, so to review what we did in order to identify this our potential function graph is we took it and went from our derivative. We identified where it was crossing the zero, the x-axis, put our zeros in, identified where it was positive and negative. That gave us our slopes for the original function. We then took a look at our second derivative. We graphed it based on the information from the first derivative. This gave us our zeros again, or our undefined points in this case. And then we identified where it was positive and negative. In this case, it was positive on both sides of our undefined point. The next thing we did is we went backwards. We took the information from our first derivative and our second derivative, and we kind of created a map of what our function is going to look like. Now, there's one correction that I want to make after kind of looking at this. The one thing that I noticed with our first derivative here is there was no open circle here, which meant that this is a lot smoother. So it probably just goes straight up here. It's going to be a lot smoother because it doesn't identify there being a sharp turn. That sharp turn would create that open circle the way that this is in the second derivative. So I think that this is going to be much more gradual, or much smoother, I should say, much smoother transition between the two functions. And so we end up with a curve that looks like this for our original function. Once again, we do not know exactly where this is. This could be way shifted up, or this could be way shifted down. Without a point to use as a fixed point, we're just creating a graph that looks like what the original function should look like.